Alright, everyone, we're going to get started. Today we have Colin White. He's going to tell us about general and robust communication efficient algorithms for distributed clusters.
Thank you, Nama. Okay, so the two most important words, I think, are distributed clustering, and then I'll explain how it's general, robust, and communication efficient. This is joint work with Pranjal Awasi and Nina Balkin. Okay, so clustering is the most common task in unsupervised machine learning. It's also a fundamental problem in combinatorial optimization. So we're usually given a set of n elements. It could be either in Euclidean space, or you could also use just the general distance metric. So say we have some social network, and then all the people have different distances. So maybe my co-authors are like one community, and certain department heads are close to famous triathletes or squash players, per se. So okay, so the goal of clustering is to partition all these people into k different clusters. In this case, they might correspond to communities. And then in some sense, we want to minimize the distances within each cluster and make sure the big distances span between different clusters. So one common way to do this is with an objective function. Common objective functions are k-means, k-median, or k-center. Okay, so now I'm going to explain what those mean. Okay, so I'm going to be talking about center-based objectives. So we want to find k different centers from the point set. And if you're working in Euclidean space, you don't need to assume the centers come from the point set. They could just be any points in a Euclidean space, and then corresponding k clusters. So the k-median objective is to minimize the sum of all the distances between each point and its closest center. So maybe for these data points, like 3 clustering would be like this, and then these are the clusters. K-means is the same thing, but just the squared distances. And then k-center is minimizing the maximum distance from each point to its center. In general, we can say the LP objective is the distances to the pth power, and then we might take the 1 over pth power at the end of the sum to kind of normalize things. Okay, so all of these objectives are NP hard to find the exact minimum, so we're going to be shooting for constant factor approximations. So there's a lot of research on finding approximation algorithms to all of these objectives. Okay, so I'm also going to be talking about a couple different variants of clustering in this talk. The first one is clustering with outliers. This is also called a partial optimization in certain settings, or for other problems. So for clustering with outliers, we can just forget z of the points. We can just ignore some of them. So z is going to be an input to the problem, just like k. And so now we find the best subset of n minus z points and minimize the k-median objective for these n minus z points. So maybe for our example here, the furthest 3 points from their center are just going to be ignored. So this is actually a harder problem because not only do we have to find the best centers, but we also have to find the best centers to ignore. So this was kind of a simple example, but in general, it could completely change the clustering to ignore some of the points. I'm also going to be talking about another variant called k-median with capacities or balance constraints. And so for this, we just add an upper bound or a lower bound to the size of the clusters that we want. Okay, so maybe in our example, this point gets kicked out of that cluster because it's too big, so it has to go to another cluster. So in this variant, the points they might not be assigned to their closest center. It could be that if some cluster is too big, some points are forced to a different center. Okay. Okay, so now finally I'm going to talk about all of this in the distributed setting. So nowadays many tasks have so much data you can't run the computation on just one machine. Also, sometimes the data might be inherently distributed. So imagine like you want to do some clustering on patient data coming from a bunch of different hospitals, and it's all spread out among like tons of hospitals. So it might be too costly to bring all this data to one place. So it'd be nice to have a clustering algorithm that we can just run in a distributed fashion across the hospitals. Okay, so I'm going to assume there are m machines, and throughout this whole talk, I'm going to assume the data is arbitrarily distributed. So no assumptions at all about what data goes to what machine. And so I'm going to talk about two simple models of distributed computation. There's the message passing model where any machine can send a message to any other machine. And this is very similar to the coordinator model where we set one machine, say machine 1 to be the coordinator, and then each machine can just send a message to and from the coordinator. So these are actually pretty much the same up to a factor of 2, because you can simulate a message passing model, or an algorithm in the message passing model by just sending all your messages through the coordinator. Yep.
Do you have any upper bounds on the size of the messages, or maybe arbitrarily large messages?
They could be large, but our goal is going to be try to minimize the communication.
Oh,
so
okay.
that brings me to any other questions? Yep.
Are you going to say more about how communication's measured? Like synchronous rounds where they're all sending, that's what you're counting? Or is
it's measured by the number of bits of communication.
Okay.
So I think in this talk, all the algorithms are going to be pretty simple, like just like one or a few rounds of communication. So we don't really need to worry about like all these like asynchrony things. But I'll discuss it further later on. Okay. So any other questions about the problem setup? All right. So again, we still want to compute like a constant factor approximation, but we want to make sure the communication's not too big. So of course one algorithm could just be bring all of the points onto one machine and then just run a regular clustering algorithm. But we want to do better. So what is known in distributed clustering? So Balkan et al. In 2013 showed a constant factor approximation for k-means and k-median. So this means, so remember I defined the LP objective. So k-median is p equals 1, k-means is p equals 2. And then the communication was MKD, where M is the number of machines, K is the number of clusters, and D is the dimension. And this paper was actually mostly focused on producing good core sets, but they also got this result for distributed clustering. Okay, so then Botany et al. Showed a 32 alpha approximation, where alpha is just your favorite approximation algorithm for a single machine, for clustering. And they showed it for any LP objective, so k-means, k-median, k-center, or anything else, and pretty much the same communication, just up to log factors. Okay, and then Malcolms et al. Studied just k-center, and they showed a 4 approximation algorithm for k-center, and also a 13 approximation algorithm for k-center with outliers. And then the communication you have to replace k by k plus z, but otherwise it's the same amount of communication. And then very recently, Guha et al. Showed a constant approximation for any, no. Oh, sorry, z was the input for clustering with outliers. It's the number of outliers. Any other questions?
So just make sure that this is number of bits and it doesn't depend on how many points there are?
That's correct, yeah. It depends on the number of clusters, but not the number of points. Yeah. Any other questions? Okay, so Guha et al. Studied clustering with outliers, and they showed a bi-criteria algorithm. So they got a constant factor approximation, but the algorithm might return like 2z outliers instead of z outliers. Or the clustering returns 2z outliers instead of z. But they were able to save on the communication. So I think that's like a MZD factor or something shaved off from the previous result. Although that one was also for case center. Okay, so there's also a lower bound on the communication needed to do distributed clustering. So also pretty recently, Chen et al. Showed that any clustering objective, any constant approximation, so even if you want to do a 100 approximation algorithm, you're going to need to communicate m times k bits. Okay.
What's M, sorry?
M is the number of machines. Okay, so in this work, we kind of bring all the previous results into one general framework, and we have all the variants and tighten the analysis and everything. So we give an algorithm that works for any LP objective, works for balance constraints, outliers, and we get this approximation is actually for k-median. For general LP, it's like a lot messier, but you can see for the k-median case, it improves over the previous results here. Okay. And then we also have a lower bound, and it's a dimension-dependent lower bound. So this lower bound it's great when the dimension's constant, but when the dimension gets really big, it's kind of a bit loose. So we show an omega mkd lower bound. And then we also, I'll discuss later on this notion where if your data looks a bit nicer, then we can get much better guarantees for the clustering returned. Okay. So now I'm going to start by talking about the general framework for the distributed algorithm. I'll just keep it simple and talk about k-median with no variance. And then I'll talk about how to modify the algorithm to handle outliers. And then I'll talk about communication complexity and then this clustering understandability. Okay, so the algorithm is actually very simple. And I should note this is a similar algorithm to the Batini et al. Paper. So we're given as input, so say machine MI has data S sub I, where all the S sub i's make a partition of all of our data. And then we're also assuming that we have a couple approximation algorithms that work for single machines that we're going to use. Okay, so now on each machine, it's going to just cluster its own data using the approximation algorithm as input. And it's going to output some centers. And then for each center, we look at its corresponding cluster and count the size of that cluster. And then we're going to assign that as a weight to the center. So now each machine has a bunch of centers and a bunch of weights. And then we send all of these to the coordinator machine. Okay? And so now the coordinator has all the centers from each of the machines along with the weights. And so we're gonna run the second clustering algorithm on all of these centers with the weights. So we're gonna run a weighted clustering algorithm. Okay. So you might be wondering why I need two approximation algorithms here rather than just one, and I'll answer that question really soon. But so this is the overall theorem we get. We get some approximation that's in terms of the guarantees of the approximation algorithms we use as black box. And then it's also pretty easy to see what the communication is because there's just a single step that uses communication. It's just when each machine sends all of its centers with the weights to the coordinator. So we assume that each data point, if we're in Euclidean space, each data point has d dimensions. We just assume each dimension is constant, so it takes d bits. And so there are m machines, each sending k data points, so it's mkd total. And then all the weights are just a number from 1 to n, so it's just log n. Okay, so this is the reason we needed 2 different approximation algorithms. It actually helps us use a bi-criteria. So remember, the first algorithm, A, is going to be run on each of the individual machines' data sets, and then the second algorithm is going to be run on overall the centers. So for the clustering algorithms on the individual data sets, we're going to use a bi-criteria algorithm. And the reason we can do that is, so by the way, for this I mean we open up more than case centers and we get a approximation algorithm. So before, when I said bi-criteria, like a couple slides ago, it was with respect to the number of outliers. But here I'm just talking about regular k-median. So now what I mean is that we're going to open up more than case centers. So there's a great bi-criteria algorithm by Lin and Bitter where you open up k over epsilon log n centers, and you can really save on the approximation guarantee. So it goes to the approximation of the clustering is 1 plus epsilon. Whereas if we just opened up k centers, it would have had to be the best known as 2.675. So if we run this bi-criteria algorithm in the first step, then we lose a little bit on the communication. So we have to communicate more centers, but that'll just be absorbed into the big O notation. And we lose like some log factor, and we really save on the approximation ratio. Okay, so then for the second clustering algorithm, the one that's run on the centers, we need a real approximation algorithm this time. So for that we can use the best known approximation algorithm and then get an 18 approximation overall. Okay. Any questions about the algorithm or the theorem? Okay.
So I guess somehow the point is that, so I guess you didn't say this, but you want to use efficient algorithms on each of the machines also. You didn't, somehow with your setup, I assumed you were going to allow each machine to just take as long as it wanted. But you're constraining not just the communication complexity, but also the running time.
Yeah, I guess I did not say that, but yeah, we hope to have all of our algorithms be efficient. Yep.
Just because I'm unfamiliar with this area, what can you explain a little? Can you explain in a little more detail what you mean by a bi-criteria algorithm?
Yeah. So okay. So regular approximation algorithms, of course, we have to return k centers, but we can't get the optimal. We have to get like the best known as this 2.6 approximation, and there are also lower bounds. Like we can never do better than 1.7 in polynomial time. But a bi-criteria algorithm is where you might return 2 k centers instead of k, and the approximation guarantee is with respect to the best clustering for k centers. So that's why you can get like a much better approximation than just 1.6. Does that kind of make sense?
So you allow yourself to pick more centers to get a better approximation on the...
Yeah. So if you look at like the sum of the distance between each point and its center, of course if there are more centers, that sum is probably going to go down.
I see.
Yeah. Okay. And yeah, so going back to the first question, we want to have efficient algorithms. I guess if we're allowed unbounded time, then we can just kind of brute force to find the optimal center. I think we would still though, if we give ourselves a limit on the communication, we can't find the optimal distributed clustering. But yeah, anyway, in this talk, we're shooting for polynomial time algorithms. Okay, so now I'm just going to give a quick example of how the algorithm works, and then I'll get to proving the approximation ratio. Okay, so the first step is, okay, so assume each color is a different machine, so maybe one machine has the purple points, and so on. So the first step is that each machine just clusters its own data, and then we get centers from that first clustering, and then we send all the centers to the coordinator, and then the coordinator just clusters all of these centers. So now each point is assigned to the overall center. So in order to bound the approximation ratio of this algorithm, we're going to need to bound the distance from each point to its overall center. So it's kind of like taking two hops, the black line and then also the red line is what we're going to have to bound. Yep.
So for the final assignment of points to centers, are you assigning based on the centers computed at the local machine, or are you doing a minimum distance to any of the final centers?
Yeah, that's a good question. So if you have balance constraints, then it turns out you need to assign it to the local center's local center. But if you don't care about balance constraints, then you actually can just assign it to its very closest. It actually doesn't affect the approximation ratio, whichever one you do. But it might lead to a better solution. Like we can't prove that it leads to a better solution, but or we can't prove the other way is better, but it doesn't affect the analysis. Okay, so yeah, to get a bound on this approximation ratio, we need to bound these black distances and also the red distances. Okay, so first I'm going to show how to bound the black distances. These are the distances between each point and its center on its own machine. Okay, so we have some lemma to do this. And by the way, I should point out, after we finished this project, we found out that similar lemmas to this stuff was known in the streaming community like 10 years ago by Guha et al. So I guess it's just another case where there's like all this independent research going on. I mean, we should communicate. But nobody handled outliers before this work. Okay, so here's what I call the local solution lemma. So if we let opt of s denotes the cost of the k-median objective on the data points of s. So the lemma says that the sum of all the k-median objectives on the individual machines is going to be at most 2 times the cost of the optimal over the entire data set. Okay, so I think there are 2 points, 2 observations we can make to kind of understand this lemma. So the first is that the thing on the left should be, like, you should think it would probably be a lot smaller than the thing on the right, because on the left we get to use m times k centers, and on the right we only get to use k centers because it's like the global optimal. But the other observation is that maybe we have a situation like this where there's some really good center, but it gets pushed to a different data set, or a different machine. So these points can't use that great center because it's on a different machine. So it turns out that this problem will just, it'll just affect us by a factor of 2. So in order to prove this, we can show that the optimal solution where the centers have to be part of your data is at most 2 times the optimal solution where you can use any center at all, even from other parts of the data. So this is the case where the centers need to be part of the data. If the centers can be anything, like in Euclidean space, then this problem goes away entirely. Okay, so and proving this is just sort of using the triangle inequality. You replace this center with the closest center in S sub I to, or the closest point in S sub I to the best center in S, and use the triangle inequality. Okay. So this is our first step in proving the main theorem, the approximation ratio, and the overall algorithm. Okay, so now I'm gonna kind of jump back to the bigger picture. So we have something like this, where this is just some data point B, and I'm gonna say that its center on its individual machine is A sub B, so that's this. And then A sub B's center in the overall clustering outputted by the algorithm is X sub A sub B. So you should parse that as the closest point of all of the centers returned to A sub B. So this is what we need to bound, the distance between each point and its closest center in the overall clustering return. So as was already pointed out, this is at most the distance between each point and the closest center to its local center. So in order to prove this, we first make this substitution, and this allows us to use the triangle inequality a bunch of times. So I don't want to bore you guys too much, but the proof is just like using the triangle inequality a tons of times until we can get this summation and bound it in terms of the optimal solution. Okay, so, but the first step is if we use the triangle inequality once, then we can break this up into two summations. The thing on the left is we can just directly apply the lemma that I just proved, because this is the distance between each point and its local center. And now the thing on the right, it looks kind of weird. The summation is over all points in the data set, but the distances are between their centers and those centers' centers. So it's kind of weird, the summation doesn't really match the distances. And this is actually why we run the weighted.
So on local machines, are you running it with K clusters or K login or like on this?
Oh, yeah. So I should have mentioned, just for the analysis, I'm going to stick to K centers, but the analysis works also for K log n centers, and that's what we use to get the better approximation ratio. But yeah, but actually our algorithm is very general. You could run it with K log n, whatever you want. Yeah. Okay, so now we're going to try to bound this. And I was saying that the reason the algorithm needed to use the weighted points is because the summation is over all the points in the whole data set, not just the local centers. Okay. So now I'll just give some brief intuition on how to bound the second summation. So it requires a lot more notation of parse, so I don't think this is like extremely important to understand all the notation. But so just I'll go over a couple of the steps. So first what we do is by construction, this sum is at most alpha times the optimal way of clustering all the local centers. And that's just straight from the guarantee of the algorithm we used. And then what we can do is we can sub out the optimal centers for the local centers with the optimal centers over the entire data set. Of course, because this thing is the optimal way of clustering local centers. But if we sub it out for the optimal clustering over the whole data set, then we can use the triangle inequality a few more times and actually bound this in terms of the optimal clustering over the entire data set. And then again, we run into this problem where the best center might be from a different machine. So we lose another factor of 2 in this step. Okay. So I think I went through that a little bit fast. It's not like extremely, it's just using the triangle inequality like several times in order to bound these red distances. Okay. Does anybody have any questions? Okay. So this is all I want to say about the K-median part of the theorem. So again, we get this approximation, and we can plug in the bi-criteria and the optimal to get the 6 alpha plus 2. Okay, so now I'm going to talk about how to extend this framework to handle clustering with outliers. Okay, so distributed clustering with outliers is actually kind of hard because if you think about it, a machine over here might have this data point that's like really far away from all the rest of its data. But from another machine's perspective, that's like a perfect data point. So what one machine might think of as an outlier could be like a great data point to another machine. Okay, so how do we deal with this problem? So what I have here is is the first thing you might think to try when you want to come up with an algorithm. And that's just replacing the step where we do k-median with outliers. So let's see what happens when we do this. So maybe we have a situation like this, where there's some cluster in the middle, and every machine thinks that its data points from that cluster is an outlier. So that cluster just gets killed as outliers. So this could be really bad when we run the overall algorithm, because then we get like a really bad approximation ratio. So I guess bad things can happen when each machine just tries to pick its own outliers. Okay. So how do we fix this? So what we can do is, instead of running k-median with outliers, we can run k plus z median on each machine. So that means that each machine is going to output k plus z centers. And the intuition is that at the very least, the k-median objective for k plus z median can always be at most the objective for k-median with z outliers. Because in the very worst case, you just make each outlier its own center for its own cluster of 1. So, but k plus z median always has to be at least as good as k-median with outliers. Okay. And then the rest of the algorithm stays the same. So in the final step, we do have to run k-median with outliers. Okay. Oh yeah, so maybe this is what happens when we run k plus z median. Okay, so this is the final algorithm we get, which I just explained on the previous slide. And so then we show that this leads to a constant approximation algorithm, and we get the same communication, but we have to replace k with k plus z now. And then we can use, as a black box, the algorithm from Chen in 2008, who showed a constant approximation for k-median with outliers. Yep.
So sorry, I got confused. So locally machines do not have outliers, like they're just doing k plus z median. So the global machine, or the master machine, that's going to come up with some outliers. These outliers are basically some centers returned by our machine.
Mm-hmm.
And now, like, what does it, like, outliers, what does it correspond to, like, in the original data? Like,
yeah, so remember, I guess I didn't mention, but it's on the slide, we still do the weighted centers. So the center that goes to the main machine, if the coordinator calls this center an outlier, then its entire cluster is an outlier. So that's why it's crucial to use the weight. So if the central machine is trying to decide between 2 points to use as an outlier, if one of them is size 2 and one of them is size 100, it has to use up 100 of its budget for outliers for it to use the 100 cluster. And
you're still going to maintain the z bound, or is it like a backtracking and use it?
yeah, still maintain the z bound. So the algorithm we run is k-median with z outliers.
So isn't it possible that you can get fractional outliers? Like, I mean, if every center has like 100 points, but your outliers were only like 5, then...
Yeah. That's a good question. So I guess we're assuming that z is not like so small, but I think
Well, are you allowed to just like have less than 0 outliers? Just like equal larger subset. It only makes your life harder, right? So like if
we can use less than z outliers too. I guess sometimes we will have fractional outliers because so we run on the weighted points, and the way an algorithm can run an algorithm on the weighted points is just by duplicating each point a bunch of times. So maybe if it exceeds our budget to use like all the duplicated points, we can just duplicate, or we can just throw out like some of them. Okay. So Okay, so we can use this result for k-median with outliers. In the original paper, they don't explicitly compute the constant, but I hear it's around 100 or so. But yeah, so our main theorem is that we get the first constant approximation algorithm for distributed k-median with outliers. Any other questions about this? This is all I want to say about distributed clustering with outliers. So next I'm going to talk about lower class. Yep.
Does this translate to a map reduce algorithm? Like,
That's a good question. So actually, in the previous work slide, there's a paper, Botany et al., and they actually worked out all the details for doing it in map reduce. Whereas I guess our paper is a bit more theoretically motivated, but yeah. So I forget, the map reduce framework is some amount of communication, and usually this algorithm will be fine. But if it exceeds it, then you can kind of fold this algorithm over on itself a bunch of times until the communication is low enough that that you can actually run it. So the number of rounds is however many times you have to run this algorithm to get minimum communication. Yeah, I would check out the Botany et al. Paper. Any other questions?
So,
Yeah.
sorry, Colin. Somehow I remembered that in your results you had said that the Z was not being hit by the M, or am I just misremembering?
Sorry, say it again. The Z is what?
So right now it's M times Z.
The communication?
Yeah.
Yeah, in your table before, somehow the M wasn't multiplying the Z.
Oh, I guess in my table before, I only wrote down the result for k-median. But yeah, for outliers, we do actually need, this is the right one.
Right.
Yeah. Yeah, so, yeah, so there's the bi-criteria result by Guha, who had the slightly better communication. And now I'm going to show that it's actually necessary. Actually, so yeah.
Back up a little.
Yeah.
The fact that the reason you ran k plus z median rather than k with z outliers is so you wouldn't kill an outlier for a particular machine, which is actually really great for basically data on another machine, right?
Yeah.
So could you still have basically the same scenario? You have a small circle of points that should normally be clustered around a point in a different machine, and kind of the mirror image in the other machine. There's really a lot of points. So if you do k plus z, say k and z are both 1. Okay? You can still take 2 points within the 2 points from the center, from the circle, right? And basically still kill the outlier, right? You wouldn't transmit the outlier to the coordinates machine.
Wait, so you have an example where
so you have
some outliers?
Two circles. Yeah, it's not doing any outlier, but the thing is, what I saw for them is the k plus z median solution, so you don't kick out the outliers, so you can still have them in the overall solution.
Yeah, basically in case what you think of as an outlier is a center for another data, for another machine.
So I think what I'm describing here seems like kind of contradict that intuition at least, right? So if you have 2 circles and a point in the middle, the points go in the wrong machine in some sense.
I see. Okay, so maybe my intuition was a bit slipping some stuff under the rug. It's not the sufficient intuition. Yeah. So I mean, as far as the proof goes, we need k plus z median to bound this in terms of k median with z outliers. Maybe. Okay. So I don't know if I can think of one right now, but there are some examples where running k plus z median completely messes you up. But for k plus z median, it's provable that it'll work out. Maybe we can talk more after. Okay. Yep.
So I just wonder, the k and z is set beforehand clustering.
Yeah.
If given a real data set, how can I set set K and Z in
Yeah.
optimal way.
So
If I don't know whether there is a cluster for one machine or
yeah, so in theoretical computer science, classically, we just assume their inputs for us. So we assume we just run it. It's a good question where if you're actually running this in real life, what do you pick K and Z to be? So I think there are some solutions. I mean, you could just try all K and see which gives the best result, and try all Z. There are some other really nice work that's like more practically motivated that show how to do smarter ways of finding the best K. But I guess for this talk, we just assume that it's given to us.
and for each machine, the K and Z is a constant. I mean, K and Z is the same for different machines.
That's correct. Yeah. Well, K is like the overall. Yeah. It's the same for every machine.
So it's possible for setting different K and Z for different machines.
So yeah. I mean, you could do that. I'm not sure if it would help you, but it's possible to do that. I guess we don't have any like theoretical guarantees on setting different K for different machines. Okay. Any other questions? Okay, so now I'm gonna jump to communication complexity. So before, when we were talking about the upper bounds on communication, everything was really simple because we just calculated the maximum amount of bits communicated. But for the lower bounds, we actually have to be a bit more precise in how we define everything. So say we're given some protocol, which you can think of it as just an algorithm, and some problems such as k-median. So the communication complexity of the protocol is over any input, what's the maximum number of bits communicated. And then the communication complexity of the problem, for instance, communication complexity of k-median or something, is the minimum communication complexity of all algorithms that solve the problem on every input. So there are a couple more quantifiers here. So we can assume the algorithms could be randomized, and then it has to answer correctly on all inputs with probability 0.99. Okay, so what this is not saying is that you just have to get 0.99 inputs correct. You have to get all correct with probability 0.99, where the randomness is over the randomness in the algorithm. Okay. So does this make sense for everyone? Okay.
So, and this doesn't require that the algorithm be pulled in real time, right? This is just about.
Right. Yeah. This slide will be all information theoretic. Okay. So I mentioned this result like many slides back, but it's already known that the communication complexity of computing any C approximation for any clustering objective is omega m times k. So you need mk bits. So this,
dependence on C in the previous round as well?
there's no dependence on C. So they actually
Any constant approximation.
What?
It's just a constant.
Yeah. So the reason is because they construct a clustering instance where there are either k points or k plus 1 points. So if there are k points, the solution is 0. And if there are k plus 1, the solution is 1. So it's like, if you get it wrong, it's like infinity. So that's why there's no dependence on C. But this does not generalize to higher dimensions at all.
So you're in this model, you have to get the answer exactly right?
No. And
So
it
you're
says
allowing
that
approximations.
it's the opposite. So even if you just want to solve 100 approximation, you need this many bits communicated. Okay. So what we show is, so actually for our result, we do assume we need to find the optimal k-means, but we get a dimension-dependent lower bound. So we show that we need mkg bits to output the optimal k-mean solution. And this is for a Euclidean space. So I'll just give some quick intuition on how the proof goes. So we use this result from Garg et al., who showed finding the mean of m points, where the m points are all on different machines, takes omega m times d communication. And so this kind of like, this result shows that the communication scales linearly with the dimension of the points. And this result is also for Euclidean space. And okay, so we find a reduction from this finding the mean of endpoints to clustering, to k-means clustering. And the way we do that is our instance of finding the mean has k times d dimensions. And so here's the idea. So say we have these points. These are k times d dimensional points, and we want to find the mean. Well, in order to reduce to a clustering problem, what we do is for every point, we split up its dimensions into k different groups. So like the black point, we just put half its dimensions here, half its dimensions over there, and so on. And so now this is the clustering problem that I am defining. So I claim that to solve this clustering problem, we need to solve this finding the mean problem. And the intuition is that we have this really nice fact in Euclidean space where in order to find the mean of a d-dimensional point, we can just find the mean of each of the dimensions individually and then just concatenate them together at the end. So there's a bit more details here. For instance, we need to make sure that like the first half of all the points are in one cluster and the second half are all in another cluster. But so we have to like add offsets to everything. But once we get that to work, we can show this reduction. Okay, so this is just the idea. All right. Any questions about communication? So no.
What can you say about approximate k-means?
Yeah. So that's a very nice question, and I think it's great future work. So here we just showed the first result that was dimension dependent, but nothing's known for approximation. Yeah.
Is there anything known about like has anyone tried to say like approximating the mean of endpoints which is like obviously easier for any
yeah, so I'm not aware of any results even for approximating the mean. They show some approximation, but it's like 1 over n, so it's like kind of bad. Okay. All right, so now I'll just quickly talk about the final part, which is clustering under stability. So this is a nice line of work where instead of assuming just any worst case instance, like we usually do in theory, we're going to assume that our data might have some nice structure, and we try to leverage this structure. So in this line of work, we make these assumptions about our data up front, and then usually you can get much better algorithms with much better guarantees than in the worst case. So here's one of these definitions by Balkan, Blum, and Gupta. And it's the 1 plus alpha epsilon approximation stability. So this says that a clustering instance satisfies this assumption if any 1 plus alpha approximate clustering has to be epsilon close to the optimal solution. And by epsilon close, I mean that the actual points in the clusters, there's only epsilon n points that are clustered differently between the two clusterings. Okay, so here's the idea. So say we have the data set on the left where all the clusters are kind of really close together. Then we can just swap a bunch of the points in between the clusters, and the objective is not going to increase by that much because the points are only like the distance to their new center is only a bit further than before. So this one will fail the assumption. But on the right, the clusters are a bit more spread out. So if we start swapping the points, we pay a lot more in terms of the approximation. So you can think of this data, or this assumption as kind of assuming that there's some clusters already in the data. So, and then you can tune these two different parameters by however much you want to assume about your data. Okay, so there are some very nice theorems in this line of work that say that under this assumption, we can get clusterings that are really close to the optimal solution, like much better than you can get in the worst case. And what we do is we show how to apply this, our same framework as before, our same algorithm as before, to this, this approximation stability model. So we take some of the algorithms from this line of work, we run it on each machine locally, we get the centers, and then we run the same algorithm on all the centers, and we get the same results as we get for this line of work. So we show that, there are theorems from this line of work where you can get epsilon over alpha close to the optimal solution, and we show the same thing in the distributed setting, with you pay a bit in the constants for moving it to the distributed setting, but we pretty much get the same results and the same communication as well. Okay. I just wanted to really briefly talk about these results, but I'm not going to go into too much details about this. Okay, so any questions? Okay. All right, so that was the last thing I wanted to talk about. So we showed a general and robust framework that handled any distributed clustering objective you want, any objective like k-median, k-means, k-center, and we showed in particular, we showed a distributed algorithm for k-median with outliers that was a constant factor approximation, and then I showed a dimension-dependent lower bound on the communication needed for distributed clustering. And also we can get better guarantees if our data looks nicer than just worst case. So I think a really good future question is, can we improve this, this lower bound? So can we get the same communication lower bound for k-median or for a metric that's not Euclidean space, or for an approximation? And then also can we find other settings where this algorithmic framework, where we can apply to this algorithmic framework? Okay. Thank you. Yep.
So I guess another beyond worst case assumption you could make is that the data is not arbitrarily distributed on the machines, which I think is pretty natural, since in a hospital geographic locations might be healthier than others, and I was wondering if you thought at all about that.
Yeah, that's a good question. I think there are other papers where they make generative models about each of about all the data going in the machine, but I didn't think about it myself though, and yeah, so yeah, but there are other papers that do this.
Any other questions?
So it seems like all the algorithms, as soon as you go to when you have the outliers, the enters into the communication in some way. Do you think that's necessary? Do you think will,
Yeah, so actually the communication complexity lower bound, the one that did not have the dimension, that one can actually be generalized to outliers. So where is it? It actually turns into m times k plus z, but it's not it doesn't depend on the dimension. So it's still a good question when the dimension's not constant, whether it's necessary. And the Guha et al. Paper I mentioned, they have a bi-criteria algorithm where they don't need the k plus z communication. So I guess we know how to solve it for bi-criteria, but still not like an actual approximation.
I guess presumably, if sometimes the dimension is going to be much larger than k, and then probably it's easy to argue that there is an omega m times d lower bound on this, right? It's just the hard thing is getting m times k times d, right?
Yeah. Yeah, I guess.
But it seems like actually in a lot of applications, md is bigger than mk.
Yeah. So I guess if you assume the dimension's high, maybe you can get a better bound. I don't know of any bounds that exist, but
I mean, certainly at least all the machines have to transmit. I mean, 1 point or something, right? So the dimensionality is large.
yeah. Yeah. So I'm not sure. So your question is.
I guess I'm just pointing out that like MD I think is somehow trivial and might be better than MK in some settings, right?
Yeah, sure. So yeah, we could think of this as like omega m times max of k and d. But then the hard part is showing m times k times d. Yep.
One I guess variant on the problem that could be natural is instead of fixing the number of outliers, if there's just a penalty for not clustering, which is kind of in the same, in other words, it's like a k-means or k-median cost, and then not clustering some point costs you 100, for every point you don't cluster. And that's just all one big cost, instead of k-means or k-median plus, 100 times the number of points you choose not to cluster. Do you have any thoughts on whether this stuff you've done might apply here as well?
Would that be equivalent to adding a center that's just like really far away? So if you choose to assign it to the center, you get this very big cost. Although in that case, you coding, you could in business would no longer be satisfied.
You can also, at any point that has that distance further than 100 to as close to center, you just mark an outlier in that case, right? That'd be another way you could just sort of.
So maybe you could just do that. So that's maybe you're saying that's like a non-outlier problem. You just create a new matrix.
I feel like you could munch it somehow to fit it into the framework.
Yeah, it seems like there are so many variants nowadays for clustering. Like,
this is similar to price connecting Steiner tree. Like Steiner tree was like.
I think price collecting is easier, right, than the version where you fix the. There you sort of add, right? So
price connecting Steiner tree is you can pay penalties for some points where you don't connect it to the Steiner tree. So you kind of say that's your version of case.
Right. Okay, so maybe that could just be handled just without even worrying about outliers.
yeah. I guess that's a good question. Actually, one question I should have put in future work is, can we do this for facility location? So that would be really interesting because then k is not fixed per machine. That actually leads to the question from earlier. So that would be an interesting variant to see if we can handle.
All right, if there are no more questions.
R38 says the same what they're doing.